Hello everyone. In this video, we are going to discuss about the hydrograph, which is used to represent the rainfall occurring in a particular catchment area, and then what are the components of the hydrograph. So let's start. So first of all, what is a hydrograph? So it is a plot of a discharge in a storm plotted against the time chronologically. That means, let's say the rainfall started with the 0 hours. So for the first hour, there was certain volume of the rainfall that has occurred. And let's say we are taking the random values for the discharge in that time period. So for the first hour, the discharge was 10. For the next hour, that is for 1 to 2 hours, the discharge increased and that has reached up to the 15 value. For the next 1 hour, this value further increased and it reached up to 20. So as the time progresses, the discharge will keep on increasing. The reason behind that is for the particular catchment area, when the precipitation is happening, when the rainfall is occurring, in that case, initially the rainfall which is occurring in a catchment area, that will be accumulated and it will be moving over the surface after a while. So initially there is a lesser flow, but once the rainfall is constant, once the certain amount of time has passed on, then the contribution of this rainfall towards the runoff will be higher, and that is why we get the higher values for the discharge. Now if we plot this discharge versus time curve, then we get this shape of the bell-shaped curve, which may be symmetric about its peak and may not be. That depends upon the characteristics of the catchment. So initially when the discharge was low, so this was the ordinates, and for the maximum peak discharge for a certain time period, we are getting this maximum value, and this maximum value that we are getting, that is known as the peak discharge, the corresponding value that we are getting on the y-axis. So this y-axis is representing the runoff and the x-axis is representing the duration. Assuming that the curve started from the 0 hours, so the time taken to reach to the peak discharge, that is known as the time to peak, and the entire time period which is taken by the hydrograph, because once the rainfall has stopped but the water which has been collected during that rainfall, that will still be present and that will take enough time to move out of the catchment area. So that's why the curve will start decreasing. There will be a fall in the curve, but that will be very slow, and ultimately we will get the 0 point again. So that will mark the completion of the hydrograph and the completion of the storm. So this time period which is representing this is known as the base period or the base time. Correspondingly, we are having this hydrograph here that is representing the rainfall intensity. So we know that the effective rainfall that we are considering, that is usually 1 centimeter, and that is occurring for the TR duration. So the rainfall intensity is usually 1 centimeter divided by the time period, and that will be in centimeter per hour. So that will represent the rainfall intensity. Now depending upon the how much time is involved in the particular storm, it is further classified according to that. So this curve that we are getting, that is known as the hydrograph, and that is classified according to the time involved. So if the entire data is collected corresponding to the entire year, then the hydrograph that we will be obtaining for that storm is known as the annual hydrograph. If we are collecting the data and plotting it to obtain the hydrograph for a particular season, then the hydrograph so obtained is known as the seasonal hydrograph. And if we are collecting the data monthly, then that the hydrograph that we will be obtaining is known as the monthly hydrograph. So that is the basic of the hydrograph. Now looking at this geometry, there are different components which are involved here. So what are those? So the discussion will be now regarding the different components of the hydrograph. So as you can see in this image, on the y-axis, the flow has been shown. That means the discharge has been represented on the y-axis, while the x-axis is representing the time or the duration of the storm, or the time which is taken by the water to move out of the catchment area. So for a particular area, let's say this is an irregular shaped catchment area. Now we mark in this catchment area that, so first of all, what is this catchment area? So the entire area which is contributing towards the flow, that is known as the catchment area. So that means this is the boundary from where the water will be contributed towards this particular stream. So from all around the catchment area, the water will be contributed towards it. So we will take a point which is exiting the catchment area. So we can say that this is the point that I am marking, that is the outlet point. And so we will write that. Now there is a particular term that is involved with the time taken by the water from the remotest point or from the farthest point. That means the point which is situated at the maximum distance from the outlet point, the time which will be taken for the water droplet to come from that point and to reach the outlet, that particular time period is known as the time of concentration. So usually that is the maximum time which would be taken by the water droplet, and that is usually equal to the base period that we represent by TB. So because ultimately the water droplet that is at the maximum distance, that will take the maximum time to reach to the outlet. Now what are these components? So when the water is flowing, when the precipitation is happening, so initially for a minute time period, there is a decrease in the flow. The reason behind that is the maximum flow that is occurring, that is not falling or that is not moving over the surface, that is going inside the surface. And that is why this segment, let's say we are denoting that as OA. So this OA segment, that is representing the base flow. Now what is this base flow? So we have seen that the runoff which occur on the surface, that is a composition of two of the values, that is the direct runoff. That means the runoff which is occurring on the surface, and the base flow. That means the flow which is occurring in the ground. So the component of these two, because ultimately the runoff will be because of these two factors. So the first component is the base flow, which is reduction. So that is why this segment is known as the base flow recession. The next segment, as we can see, is the rising part or the rising segment of the hydrograph. So let's say this point is B. So this AB segment, that is known as the rising limb or the rising segment. Corresponding to this, we will mark the similar point on the other side, from which we can say that the curve has started falling, and the segment between these B and C point, that is known as the crest segment or the peak of the hydrograph. Now when we reach the point C, it has been observed that the curve is starting to decrease. So from that point and till the point the base flow is contributing, that segment is known as the falling limb or the receding segment. And again after that, as we were obtaining the initial part of the hydrocurve, as we were obtaining in the initial phases of the hydrograph, the same segment is obtained where the base flow is reducing, because the contribution towards the runoff is from the base flow, and that is why this segment is again known as the base flow recession. Now in this point, the curvature is also important. So we have seen that this maximum discharge that we are getting corresponding to the peak value is known as the peak discharge and is represented by QP. Now the curvature for the rising limb and the falling limb, both of these curvature are concave in nature. This is also concave, and this BC portion and the nature of this BC portion, that is convex, because that is outwards is convexity is present. Now the points where this curvature is changing, that is a mathematical term. So the point where this curvature changes, that is known as the point of inflection. So corresponding to a hydrograph with a singular peak, we will obtain 2 points of inflection, and if there are number of peaks, then the point of inflection obtained will be corresponding to that. Similar to these terms, there is one more term. So when we plot the hydrograph, this hydrograph is obtained here, that is representing the rainfall. So rainfall is for a shorter duration, the storm occurs for a lesser duration, but the implication of that, that is obtained in the form of the runoff, that is evident for a long duration. That is why this hydrograph will be for the shorter duration. So from the center of this hydrograph, the distance of the crest of the, from the center of the hydrograph to the peak of the hydrograph, the duration which is taken here, that is known as the time lag, or the, that is represented by TL. Now this completes the all the components of the hydrograph. Now there are different factors which affect this particular shape of the hydrograph, and broadly we classify these factors in two categories, that is the climatic factors and the geographical factors. So one by one we are going to discuss that what is the implication of these factors on the shape of the hydrograph. So the first one is the climatic factors which affect the shape of the hydrograph. So first one is the intensity of the rainfall. Now if the rainfall is intense, then obviously the rainfall that is occurring, that will be at higher magnitude. So in that case, initially the curve that we were getting, this was the rising limb. So now we will be getting the steeper value of the rising limb, because more runoff will be obtained in the shorter duration because of the higher intensity. So that is corresponding to the higher intensity, and we will be getting the steeper rising limb. So that means this intensity of the rainfall, if that is high, is having an impact on the slope of the rising limb. Similarly, duration of the rainfall. So if the duration of the rainfall, if that is more, so the storm that we will be getting, that will be also for the longer duration, and because of that the runoff contribution from the stream, that will be for the longer duration. So the curve that we will be getting, that is the hydrograph, that will be having the more wider base. That means this base period will be increasing if the duration of the rainfall is increasing. Then the magnitude of the rainfall, that will be again the same, that will again be the same as was the first case, that in case of the magnitude increment, the curve that we are getting corresponding to the rising limb, that will be steeper. And then the movement of the rainfall, that means the runoff. So if the runoff is contributing early, if the movement is faster, then the peak that we will be obtaining, that will be quicker, and the steeper curve will be obtained, because initially the contribution towards the outlet point, that will be very fast. And on the other hand, if this movement is slow, then the peak that will be obtained, that will be at a later stage, and the curve that we will be getting, that will be relatively flatter. So if the faster movement is there, then this curve will be something like this, and if we are obtaining the slow peak, then this will be the curve that we will be getting. So that is the impact of the climatic factors. Now in total, all of these factors are having majorly the impact on the rising limb of the hydrograph and not on the other segments of the hydrograph. Then the next category of the factors which affect the shape of hydrograph, that is classified as the geographical factors, which are important ones. So first of all is the shape of the catchment area. That is very important aspect as far as the hydrograph is obtained. So we will obtain the hydrograph for the different shapes of the catchment area. So I'm plotting these four type of the shapes of the catchment area, corresponding to which we will be obtaining the different hydrograph. Corresponding to which we will be obtaining the different hydrograph. So this first shape, that is known as the fan-shaped catchment area. The next one is the elongated shaped catchment area. So this is the elongated shaped catchment area. All of these are having the outlet point in the same direction. This is the elongated one. Then the leaf of the catchment area, that is in the shape of the narrow leaf, that is also having the catchment area as the outlet point in the same direction. And if we are having the leaf with the two of the broad areas, so that is the another point. Now corresponding to all of these, we will be obtaining the different shapes of the hydrograph. So starting with the first one. Now this will be the plot between the discharge and the time. So we will be getting this as the shape of the hydrograph. Now the time taken by the curve to reach to its peak, that is the time to peak, that is TP, and that is the standard value of the hydrograph. That is the standard shape of the hydrograph that we obtained for the fan-shaped catchment area, because the contribution from each of the point towards the stream, that will be at the almost the similar time. But if we take a look at the elongated catchment area, now for this remotest point to reach to the outlet, that will take the maximum time. Similarly, the points which are near to this remotest point, that will also take a very huge time. So because of that, this curve that we obtain, that is usually flatter, and this is the time which is taken to peak the hydrograph. So in comparison to the fan-shaped hydrograph, in comparison to the hydrograph which are obtained for the fan-shaped catchment area, the hydrograph for the elongated catchment area are flatter. because the time taken by the water droplets to reach the outlet point is more. Then if we are having this narrow leaf, so the points which are situated near to this outlet point, that will be taking lesser time to reach this point, but the points which are at the farthest distance, they will take the maximum time. And because of that, the peak that we obtained, that is slightly shifted, and there is some skewness in the curve, and this is the shape of the hydrograph that we obtained for such type of the catchment areas. Then similarly, for this shape of the fourth shape of the catchment area, the first part of the catchment area will be contributing towards the outlet point quicker than the contribution from the backside. And because of that, the shape that we get for such type of catchment area is involving the two of the peaks for the hydrograph. So this is the impact of the catchment area. There may be more number of the catchment area which may be available. So all of those plots of the hydrograph, they are obtained in the similar manner. The next factor is the size of the catchment area. So if the size of the catchment area, if that is bigger, then obviously the peak that we will be getting, that will be at higher discharge. So for example, if let's say this is the hydrograph that we are obtaining for catchment area which is having an area of 100 square kilometer, and corresponding to this, if we are having an area of 20 square kilometer, so the correspondingly the curve that we will be getting, that will be somewhat like this or even below this. That means the correspondingly the discharge that we will be getting, that will be roughly 0.2 times of the peak discharge that was obtained for the 100 square kilometer. That will be the impact of the size of the catchment area. Then the slope of the catchment area. So the slope of the catchment area, if that is higher, if that is very steep, then the contribution of the runoff towards the outlet point, that will be quicker if that is steep. On the other hand, if that slope is almost flatter, then the contribution or the speed with which the runoff will be moving, that will be slower, and because of that the contribution towards the outlet point will also be slower. So that is the impact of the slope of the catchment area. Then the next factor is the drainage density, and that is a ratio of the channel length to the drainage area. That means in a particular catchment area, how much length of the channels are available, that is representing the density drainage. That is representing the density of the drainage. That means to take the water from the entire catchment area, how many channels are available. If the lesser channels are available, that means it would take the huge amount of time to reach to the outlet point. And on the other hand, if we are having more number of channels, then the contribution towards the outlet point will be quicker and will be more. And therefore, for the more drainage density, we will be getting the higher peak, and the peak will be obtained at the quicker point of time. Then the last point is the land use or the vegetative cover. So this act as the hindrance to the flowing path of the runoff. If the more of the vegetative cover is available, that means the obstruction to the path of the water will be more, and therefore the contribution of the water towards the outlet point will be lower and will be at the slower rate, and because of that the peak obtained will be lower and will be obtained at the later stages. So that completes the discussion regarding the all the factors and the concepts of the hydrograph. In the next video, we will take a look at the flood hydrograph and how we separate the base flow from the flood hydrograph. Thank you.